then the piston skirt is a graphol, or basically a graphite coating, just to reduce friction instead of the ferrous coating. We still use MALA for all of our race pistons. Most of the NASCAR guys do these days too, and about half the F1 IndyCar engine development guys use them too. So MALA has a motorsports piston division. They're forged, they're not like the cast streetcar pistons that come in your car. They're about twice as much money, but they have a really, really good research facility. They do really cool things too, like they'll do structural failure analysis for you and wear analysis and send you back reports, and so you can run an engine, you know, for like 500 hours on a dyno, send it back to them, they'll tell you how to redesign the piston to make the piston more reliable.
Nice.
You have to be willing to do the hours and send them the parts, and you got to build another motor, and they'll recommend a change. You'll do 500 hours again, and so part of the reason that the V10 motor took 2 years to get done was we did 4 prototypes, ran them 250 miles a piece, took all the parts back and sent them all the parts manufacturers and let them write a report of what was wrong, and we changed them all and did it again. Again, that's how we can guarantee the thing for 4 years and 50,000 miles. And a lot of little things came out. For example, on the V10, the load was so high that the wrist pin would oval. So when the cylinder fires, it actually ovaled the pin.
Temporarily deflection?
Temporarily deflection, yeah. It didn't permanently flex back, but it left 4 little contact marks inside the pin bore. And ultimately what happens is that spreads the pin board so you get a crack, and the crack will migrate to the piston crown. We've had that happen in race engines before, right? And then you wind up with a catastrophic failure, but it doesn't happen until 40 or 50,000 miles down the road. But the only way to catch that kind of stuff is you literally saw the piston in half, and you put it under a microscope, and you look at all the bits, right? You know, so it's, anybody can go buy a set of pistons and throw a motor together. That's easy, okay? What, you know, BMW does the same thing. I believe BMW's tests are 500 miles, ours were 250, I believe. But they run an engine, take it apart, measure it, and this is why they run the Autobahn for 150,000 miles, because they've done, you know, 5 years of research of building engines and taking them apart, figuring out all the weak places and fixing them. Nobody's perfect, you know. Once in a while they make a mistake, like the S54 motor in the M3.
Right.
You know, but they try hard. We try hard too. Everybody's human. When we do fitment checks, we have a machine called a rapid prototyper. We'll show it to you when we go through. Anybody know what a rapid prototyper
Yeah,
is?
the one that he designs it for you.
Yeah, we didn't design it, just grows it. So you take a SolidWorks solid modeling program, and after you do your finite element analysis, you hit 3-dimensional print. And it actually takes pieces of plastic and stitches them together and grows the part off your CAD file. So this is a physical representation of your drafting, essentially. And then you can put these parts together. This is Ferrari parts, by the way. See, this matches the piston. And you can turn the engine over, check the piston, the valve clearance, and everything before you pay for tooling for the parts.
Nice.
So we build everything out of plastic on the rapid prototyper first. And then we fit check it. If it's an intake part, we actually dyno it and run it, because there's no stress on it. So the colder intake on the V10 out there, the plastic air boxes, those are actually rapid prototype air boxes, and you design them over and you change them and you change them. I think we went through about 20 iterations, and you pay the $100,000 for the hard tooling. You don't want to spend $100,000 of tooling on plastic to find out that it doesn't fit, or, you know. So the rapid prototyper enables you to solve all those problems before you go into production.
Saves you time too.
Yeah, it saves time and improves the quality. We run through a lot of these things.
Is it 100% accurate?
Yeah, it's down to the thousandths of an inch. You know, like the, you know, like the part is. Let me show you something else here. This is really cool. Okay.
Steve,
Yeah.
when that pin ovalizes, does that necessitate you to use a different material?
No, it's still standard steel. We just make the pin's wall thicker, or you can make the pin diameter bigger. But when you make the pin diameter bigger, you have to move the piston up in the bore and make the rod shorter. And that makes more friction because of the rod angle. So the best solution is to make the pin thicker wall. The wrist pins in the race engines are really small. They're not like streetcar wrist pins, and they're really short in order to save reciprocating mass. So you're always pushing the envelope on them. So then pin ovalization becomes an issue. So this is our racing oil pan. And I think most dry sumps you see, a guy will weld a fitting in the side of a wet oil pan, or it'll be a sheet metal pan, like one of those Milden pans or something like that. We have a complete billet pan, and the billet pan is actually a stress member in the block. It has little girdles across all the mains. It's super low profile. This is how we lowered the engine 2.5 inches in the car. And then we CNC passages to the scavenge stage of the pump, a little O-ring on here, and that's how we seal the whole thing. We have a separate scavenge stage for the cylinder heads. So we run this up to the cylinder heads. It pulls oil out of the cylinder head so it doesn't puddle up when you go around corners at 2 or 3 Gs. Okay? And then to make it really cool, normally a dry sump will have hoses that go to the engine, and those hoses can fail and they weigh a lot and they melt on headers and things like that. So we run these patches, eliminating all the hoses, and the oil pump is actually bolted directly to the oil pan with O-rings, just like that plate is on the bottom. So this is what the system looks like when it's done. Isn't that clean? And then this is where the supercharger lobes are inside here. So every one of these sections has a scavenge pump in it with a supercharger lobe on it that creates a vacuum and pulls all the oil out of the bottom of the engine. This is called the dry sump, because we take all the motor out of the oil and put it in a tank. So now we just have one hose going to the tank, one hose going back to the tank, and one hose going in to feed the engine galley. So you have 3 hoses on the dry sump. Instead of you'd have, this is a 5-stage pump, you'd have 5 more hoses going in here. Reduces a lot of weight. And then in order to save weight, also, we don't have a tensioner on the belt. Normally you have a tensioner on the belt. We have it so that when it's cold, the belt is slightly loose, and when the pan gets hot, it expands and the belt gets tight. And this saves us from putting a tensioner on the belt. We save another 1.5 pounds on the tensioner. This is how you get the 79 or 89 pounds out of an engine. It isn't by, there's 189 part on bolt, right? You take every single part of the motor, you take a pound or 2 out of it. Okay, and when you're done, you have 89 pounds. This is like 5 years of a pound here, 1.5 pounds there. That's how it adds up. So the dry sump system added 22 horsepower to the engine, took 15 pounds off the engine just by itself, and lowered the engine 2.5 inches in the car. So this is a really important key element of the research. Expensive part.
Is it a very light vacuum as far as like you think if it was a strong
It's like
vacuum?
14 to 16 inches.
Yeah.
It's pretty high.
I mean, obviously that it gained horsepower, so it pulling on the pistons that are trying to go on the upstroke, it doesn't really.
Well, actually,
it outweighs the advantage.
You actually put it on a vacuum, so there's actually no drag on the engine at all, really. The pumping loss from the piston going down is way greater than the vacuum from going up. So this is what the lobes look like on the inside. And by the way, we can also tune the lobes. I know, so this is how you get this horsepower. Well, every time this lobe pushes oil, it takes energy, right? If the lobe fits exactly tight in the piston, it's what's called a positive, or in the bore, it's a positive displacement pump, where every time the pump turns, you get that amount of oil. But if you make the lobe a little bit short, oil can bypass around the outer edge, and the pump becomes less efficient. Okay? Actually, less efficiency makes more power. What we do is we figure out how much oil flow the engine needs. This is one of the ways we found more power, by taking the oil passages in the engine one by one and restricting them until the part downstream galls from not enough lubrication. You get wear on the part from not enough lubrication, and you make the hole one size bigger. Now we put a meter on the pump that measures how many liters of oil we move per minute into the engine. Okay, and then we figure out how many we're consuming after we restrict these parts, and then we slow the speed of the pump down or change the size of the lobes, so we pump just enough oil for the engine. Then we're not taking any energy moving excess oil around. This is how you find another 20 horsepower. It goes on like this, right? This is endless amounts of tedious research is what this is. It's not just, everybody thinks you make horsepower by just throwing a big cam in and more compression. You can do that, by the way. But there's a whole lot more to it than that, right? This is why Formula One motors are making 800 horsepower with a 2.4 liter engine. This kind of stuff, right? It's not that like cams are any bigger than they were in the 1980s, or there's any more, nobody reinvented compression from the 1980s. All the gain in horsepower we have in the modern engine, either the street car or a race engine, is due to efficiency gains in the design. Just understanding the science of it better.